good morning students. I am Vaishakhi Shah from LJ Institute of Engineering and Technology. Now in our subject Fluid Mechanics and Hydraulics, in chapter which is called Flow Through the Pipes, in today's lecture we are going to study Hagen Poiseuille equation. Okay, Hagen Poiseuille equation is basically equation which is used to find out head loss due to friction for laminar flow. Okay, so in this equation it is normally used for viscous fluid and flow through a circular pipe. Here flow of fluid must be from circular pipe. Okay, so the flow through the circular pipe will be viscous or laminar if the Reynolds number is less than 2000. For the Hagen Poiseuille equation, the flow should be laminar flow, and for the laminar flow Reynolds number must be less than 2000. Okay, in Hagen Poiseuille equation we have to consider a circular pipe. Here you can see in this figure that we are considering a circular pipe, and in a circular pipe the radius of circular pipe is capital R. In this pipe we selected an element, a small element of fluid itself, and radius of that element is small r. Okay, clearly you can identify that dimension in this figure, that you consider a circular pipe. In a circular pipe the radius of pipe, that is capital R, and radius of element is small r. Here we selected a element. Here that highlighted part is your element which we selected, and the element is A, B, C and D. You selected element A, B, C and D. Okay. Now length of this element is delta x. Length of selected element is delta x. Radius for this circular pipe is capital R, and radius for this selected element ABCD, that is small r. Okay. Now in this diagram, as you can see, on surface AB, the pressure acting on surface AB, that is P. Pressure on surface AB, that is P. Now on surface CD, the pressure acting on surface CD, that is P plus del P by del X into del X. Pressure on surface CD is P plus del P by del X into del X, that is pressure on surface CD. Clear? Now as we know that force equals to pressure into area. Force, that is pressure into area. If we have to find out pressure forces acting on this element, then pressure force acting on this element are: first, pressure force on surface AB, that is P into pi r square. Pressure into area, P into pi r square on AB surface. Clear? Now on surface CD, the pressure is P plus del P by del X into del X, and area of circular pipe is pi r square. So pressure force on surface CD is P plus del P by del X into pi r square. Now the third force, which is shear force, is acting on A, B, C and D. Then the shear force is tau, which is acting on area 2 pi r into delta x. So the third force acting on this element is, as you can see in this figure, the third force acting, that is shear force at area 2 pi r into delta x. So the third force is pi tau into 2 pi r delta x on the surface of the fluid element. Clear? So three forces are acting on the element A, B, C and D. Clear? Now at equilibrium condition, summation of all three forces must be equals to 0. For equilibrium condition, summation of all three forces must be 0. So, taking summation of all three forces, the first force is P into pi r square in this direction. The second force is P plus del P by del x into delta x into pi r square on surface CD, that is in opposite direction. So, pressure P is positive and the pressure on CD we are taking as a negative. So, P into pi r square minus P plus del P by del x into delta x into pi r square minus the third force is also in negative direction, which is tau into 2 pi r into delta x, which is equals to 0. So, now by rearranging this equation, you get that minus del P by del x into delta x into pi into r square. By open this bracket in your first equation and minus 2 pi r tau into delta x equals to 0. Okay. Here delta x and r is cancelled. So, your equation is minus del P by del x into small r minus 2 into tau equals to 0. Now, making subject as a tau, taking tau as your subject, then tau equals to minus del P by del x into small r by 2. This is equation for tau. Tau is your shear stress and this equation is your equation number 1. Now, first in Hagen Poiseuille equation, we will find out velocity distribution. So, velocity distribution, as we know that Newton's law of viscosity, tau equals to mu into du by dy. This is Newton's law of viscosity. So, this is your diagram for circular pipe. As we know that capital R is a radius of circular pipe and small r is a radius of your element A, B, C, D. If we are taking difference of these two radius, then capital R minus small r is indicate as y. We will indicate the distance between capital R minus small r by y. So, here y equals to capital R minus small r. Okay. So, if we are taking differentiation on both the sides, differentiating on both the sides, then differentiation of y, that is dy, here dr equals to 0 and small r that is minus dr. So, taking differentiation on both sides, you get that dy equals to minus dr. Now, see the equation of Newton's law of viscosity, where tau equals to mu into du by dy. What if we replaced dy by dr? Yes, you can replace dy equals to minus dr. So, your equation become tau equals to minus mu into du by dr. We replaced dy by minus dr. Okay. The equation number 1 is for tau. Here tau is called shear stress. So, tau equals to minus del P by del x into r by 2. That was your equation number 1. We again derived that tau equals to minus mu into du by dr. We derived both the equation for tau. So, you can place the value of tau in equation number 1. So, put the above value in equation number 1, you get that minus mu into du by dr equals to minus del P by del x into r by 2. Clear? Replacing value of tau in equation number 1. So, rearranging this equation, you get du by dr equals to 1 upon 2 mu into del P by del x into r. You get the equation for du by dr, that is 1 upon 2 mu del P by del x into small r. Now, integrating above equation with respect to r. Remember that we are taking integration with respect to small r. So, integrating above equation with respect to r. You get this equation u equals to 1 upon 4 mu into del p by del x into r square plus c. Here we are taking integration with respect to r, and here plus c is a constant due to integration. So, our equation of u is 1 upon 4 mu into del p by del x into r square plus c. Now, if we have to find out value of c here, then we have to apply the boundary condition. Okay, remember that at which place the velocity is 0 in a circular pipe. If fluid is flowing in a circular pipe, in this flowing fluid, at which place velocity is 0? Okay, velocity is 0 where small r equals to capital R, means at the edges, at the surface of the pipe, the velocity is 0. So, applying boundary condition here replaced small r equals to capital R. So, your u equals to 0. Your equation become 0 equals to, because u is 0, 0 equals to 1 upon 4 mu into del p by del x into capital R square. Remember, here we replaced small r with capital R. So, capital R square plus c. Now, in this equation, if we are making c as a subject, then your equation become what? Yes, c equals to minus 1 upon 4 mu into del p by del x into r square. Now, in equation of u, which is 1 upon 4 mu del p by del x into r square plus c, place the value of c in this equation. So, you get u equals to 1 upon 4 mu into del p by del x into r square, and the term c, which is minus 1 upon 4 mu into del p by del x into r square. Clear? So, this is your equation. Now, taking common terms, then u equation for u, that is minus 1 upon 4 mu into del p by del x, this is constant in both sides, into capital R square minus small r square. This equation is to find out velocity, which is indicate as u. So, u equals to minus 1 upon 4 mu del p by del x into capital R square minus small r square. Okay. So, this equation is equation for parabola, and the velocity distribution in pipe is also in parabolic shape. Okay. As you can see in the diagram, when fluid is flowing in a pipe, the maximum velocity of fluid is at center, and when you are going to the edges, the velocity decreases and becomes 0. So, the maximum velocity you get at center, and on the edges the velocity is minimum or negligible. So, you take as a 0. This indicates that the parabolic shape indicates that velocity at center is maximum. So, u maximum at center and u equals to 0 at your boundary conditions or at your edges of the pipe. Okay. So, here we found velocity distribution by using Hagen Poiseuille equation. Now, in our next session, we will find out the another part for Hagen Poiseuille equation in detail, and we are going to study that ratio of average velocity to maximum velocity in our next session by using Hagen Poiseuille equation. Okay. Thank you.